Okay, so in this video, I'm going to cover basic statistics in R, adding on to my video from last week about basic concepts in R. So this is really getting into a statistics course and learning how to do summaries and means and standard deviations. Alright, and please excuse my voice, I have been sick for a week and a half. What we're going to do first is to sort of a recap. So from my class last week, or if you've been watching the videos in order, you should be able to import a data file from CSV, so importing Excel type files, calculate a summary of the variables using the summary function, calculate the variance and the standard deviation using the var and SD functions, calculating z-scores using the scale function, histograms or hist, and a frequency table is the table function. So should be able to do all those things at this point, and also the mean. And we're going to add to that and talk about how to calculate standard error and confidence intervals. So we're going to take this and build some more things on top of it. All right. So I'm going to talk about subsetting and t-apply, and only a small piece of subsetting. Standard error, the length function, which allows me to do degrees of freedom and standard error. And then that leads me into confidence intervals for z-scores specifically, and then effect size and a little bit of gpower. If you're interested in more of gpower and you're in SPSS, almost all of the videos from last spring have gpower with their specific test type, and that will be coming if you're trying to do it in R. I know you can do power in R, but I really love gpower. I've been using it for a long time, and so I'm going to continue to use it because it's a great program. So the point of subsetting is to create yourself a smaller data set with a specific set of criteria. If you've watched some of the previous videos, you've already seen subsetting with the subset function, but just to show you again, it's a really great way to section out your data. And so we're moving towards data screening, and how do I look at data in R. And subsetting is going to be a crucial tool to be able to do that. So I have this little note, there are videos on object types. The way that you subset depends on the type of variable you have saved, so go watch that. And then it goes more over subsetting, like how to pull out numbers. So it's actually going over a lot of calling, how do you call variables. But it becomes super important to understand subsetting as we go. So the easiest way to me, until you get the hang of the square bracket operators, is the subset function. Because it seems rather obvious what it's doing, it's pretty mnemonic. So the way subset works is that you do subset, open parentheses, the name of the data set you're trying to subset, or the thing you're trying to subset, and then what are you trying to do with the subset, and then there are actually other options. So anytime you see ... it means there are other options, but they're not required. So you can subset out your data set and only pick 2 columns, for example. So you could select specific columns. Not going to go over that right now, but it is an option, which you can look at in the help feature. So before I get into how to do that in R, let me talk about logical operators. So logical operators are ways to select different items, or different participants, rows, if you will, based on the values that are stored in them. So what we're going to do is we're going to tell it to subset and look in each row and pick out the people that meet this criteria. So you have to come up with some sort of logical operator. So this means it makes it a true-false, and it will pick out the trues. Okay, so you can do greater than, which is the little alligator eating to the left. You can do less than. You can do greater than and equal to, and less than and equal to by adding the equals. Straight equal to, so say pull people who have a score of 4 is 2 equals. If you only do 1 equals, R does not do what you would expect to do. It doesn't give you an error. It looks like it runs, but it does not do what you want. So make sure anytime you're asking if something is equal to something, it's 2 equal to signs, not 1. Okay. The 1 equal is reserved to setting things equal to a specific variable name or something like that. Don't use 1 equal. The OR symbol is, if you're on a standard American keyboard, above the enter key, and you have to hit shift to get it. On Windows machines, it looks like two little lines. On my Mac, it looks like one straight line like this. But that allows me to do multiple operators. So I could do find all participants who are male or have a score of 45. Or I can do find all participants who scored above 4 or above 10, or below 3. That wouldn't be a very good one, but you can do combinations of variables. You can also do and. So find all participants who are this and that. So it allows you to select multiple things. If you're familiar with other coding languages, sometimes it's double and. Don't do that either. I have a hard time making sure I don't do that because of my previous programming knowledge. Okay. So let's try it. So I have a data set that I'm going to load called cheese. And I'm going to import that. So I'm going to use the import function from text file. Okay, let me find it. And so if you're learning how to import files, you can also watch one of my previous videos where I really talk about working directories, and that'll actually make your importing stuff a lot easier, so you don't have to do this every single time from the import command. You can start typing it instead of clicking on all the buttons, but it's also pretty easy to click the buttons. So I'm going to call this data set cheese data. Now it's going to be slightly different from what I have in the notes here, because I realized in class that having something called cheese was really confusing to students, because I like to use cheese examples. So let's call this cheese data, or we can just call it data if we want. But to make that clear that this is the data set and this column in here named cheese is something else. So I'm going to hit import. It shows me the data set. And then if I wanted to keep this for future use, I would copy my data line here, because this is how I imported the data. Alright, so I have a data set named cheese, and it's got two variables. So this is a data frame, which means it's a multiple columns. And the columns can be different types, so let's look at the types here. It imported the feelings variable as a factor type because I had it labeled as text. So you look at my feelings variable here, I've got it labeled as yummy and blah, so people who like cheese and people who don't like cheese. And it automatically changed that over to a factor variable because it's text, which is useful because that's how my experimental and a control group kind of thing. If you're importing from things like Qualtrics, you can tell it to give you the text labels, but that's not always the best idea, because let's say you have a bunch of 1 to 5 interval type scales where it's strongly agree to strongly disagree. It will import those as factors, and that will make it cranky sometimes if you're trying to run them as continuous variables. So you can change variables that are labeled as 1, 2, 3 to factor variables using the as.factor function. And I explained that in one of my other videos, but it will let you convert the variables from one type to another. I always recommend, if your variable is actually factor with group labels, to make sure you add those in some way. So later when you're looking at the data, you're not sitting there going, okay, which one was male, which one was female again, because you may not remember. The other variable imported as a numeric because it's got decimals, and so it's labeled cheese. So the fake data that we're working with here is we have two types of people who like cheese, people who don't like cheese. And then we give them a new fancy cheese and we ask them to rate their feelings about this new cheese. So this is data about cheese, because I like silly examples. Alright, I'm going to do a summary of this data set to see what it looks like. And I can tell you again how much I love the summary function. So let's do summary of our cheese data. And so the greatest part about summary is that it looks at the type of data that you've given it and figures out the best way to display it for you. So it does not give me the mean and the mode of, the mean and the median of a factor variable. It says you got 15 each. So it actually gives you the same thing the table function would do. So if I did the table function of that column, my feelings column here, actually gives me the exact same output. So anytime you import a factor variable into summary, it gives you a table. If you import a numeric variable, it gives me the basic descriptive statistics. So min, max, quartiles, median, and mean. All right, so I know how the variables are imported. So subsetting the data is really useful if you want to, say, data screen your two groups separately. There's a lot of people who suggest doing this, treating them as two separate groups and screening them as separate groups because that was the point of your study. I don't always do my data screening that way, but it allows you to do that. So I'm going to take two paths here. You can subset the data and then run descriptive statistics on those subsets. Or you can use tapply. So this is an or path. You wouldn't want to do both because tapply won't work if you subset first. So we're going to talk about here's how I'd subset, and then I would do all of these different, like calculate the mean, the standard deviation, that kind of stuff on each data set separately. Or you can use the tapply function, which sort of, the purpose of it is to do that where you don't have to subset. And I just really wanted to go over subsetting because it becomes so important for the next couple chapters. So it's kind of a, hey, by the way, you need to learn this. So the way the subset works, just type this out, is that first you need to save it or it's just going to print it out for you. So I'm going to call this the BLAS data set because that's the group we're going to pull out. And I'm going to do subset. First thing is the data set name. So in this example, I've called it cheese data. And the second part of the logical operator. So helpfully our studio has told me it's ... which is not useful, but what you're supposed to do is tell it how do you want a subset. That's generally using a column name. So let's do feelings equals, oops, let's spell feelings correctly. There we go. Equals to, so double equal sign, and I'm going to do BLAS. And because we've coded this, it automatically imported as factor, I could actually treat that as BLAS because that's the label for the group, or I could treat it as a 1. Do know that whatever, when it imports, it picks the alphabetical 1 to code as 1. So if you want to recode yummies as the 1 group, there's a different function that'll re-level for you, I think is the right one. It's not recode, I think it's re-level. That is in the car package, or maybe recode's in the car package. Anyway, we'll get to that at some point. I'm going to talk about switching the order of the levels because it will automatically do them in alphabetical order. So I could treat this as equal to 1, no quotes, or equal to BLAS. I know that they're called BLAS, so I'm going to go with that. So what did that do? Well, if I take a summary of that, what it did was it calculated my, it subsetted the data into a separate group with only 50 people. So it pulled all the blah people out, as seen here, and left all the yummy people alone. So I still have my original data set with 100 participants, but now I have this 50-person data set. So what I could do now is calculate the mean for my cheese variable on the SD. So this is all stuff we did last week. So I can look at my mean and my standard deviation separately for that data set alone. The other thing I'd want to do is calculate it by my other group. Spelling today. Cheese data. And let's do feelings equals yummies this time. And then I could do the same thing. Calculate the mean of the yummy group for cheese. Okay, so they think it's only a 29 rating. Oops, sorry. And then the standard deviation, because you need that to get to standard error, is 11 points. So it's got a bigger spread. The people who don't like cheese actually rated this new fancy cheese higher and the smaller standard deviation than people who do like cheese. Okay. So that is how you would do descriptive statistics if you wanted to separate by group. So lots of experimental designs include groups, and then lots of statistics include groups, like t-tests, ANOVAs. You can do ANOVA and regression are the same thing mathematically, so you can do categorical variables in a regression with other continuous variables, and let's say you wanted the descriptives on those. And so when we get into running t-tests and ANOVAs, it becomes important to know how to calculate the standard deviation and standard error, because often the summary statistics that you get back include just the means. And so you need to know how to be able to get these other numbers that we traditionally report in write-ups for like a table or your report or a picture. If you want to make a plot, that's next week's notes. So this is building on like, how could I calculate these things? Right? So you could subset the data. This is one path, and calculate descriptive statistics on the subset of data. That will take you a little longer, especially if you have conditions. So let's say you've got multiple variables. So instead, let's talk about t-apply. All right, so we did this. Oh, quick note, make sure you check and see that the subset did what you expected. So let me show you when it doesn't. So let's say I screwed this up and I only included one equal to sign. So watch over here. It's got 100 participants in the cheese data because there's 50 and this was got 50 because I did it correctly. If I run that, it actually does not give me an error or a warning. It just runs. And then it gives you everybody. So this data set, cheese data and yummies are exactly the same because it needs to be a double equal sign. All right. So that's the make sure it does what you expected it to do. All right, did this one. Oops. Okay, so why subsetting? Well, lots of reasons. It allows you to cut out bad data. So let's say you have some participants that just typed 7 the entire time. You could cut those people out. It allows you to cut out data points that are inaccurate. If you're working with response times, it allows you to trim the data. It allows you to pick only a specific group of people if you're only interested in one group over another or a specific subset. But then it leaves the original data alone. So you can create new on-the-fly data sets with only a smaller group of people. All right. Instead, I'm going to recommend, if you're calculating descriptive statistics, t-apply with groups. The important part about t-apply is it has to have some sort of factor variable. I mean, there's a whole family of apply functions. Supply, t-apply, l-apply, s-apply, and m-apply. And so they all have the same basic concept that they do things instead of including loops in your data, and it runs a lot faster, but they do it in different ways. So t-apply cannot be used when you don't have a grouping variable, because the point is that you have some sort of factor variable. If you have just a bunch of columns, the apply function is a better one for that. And we'll be getting to apply probably in the data screening section, so a couple weeks. The trouble I have with these is the descriptions of them in the help don't always make it obvious what you should do, because they're fairly complex functions underneath the hood, I think. So I think QuickR's website has a really good example of them, but they're better to learn in action, so let's try them. Okay. So t-apply allows me, the point of it is, and the T stands for table, specify a grouping variable to split the data on, or grouping variables, so you can have multiple ones, and then calculate anything. So you can actually calculate multiple different things using t-apply, but generally I would think of this as a descriptive procedure. And anytime you are looking at the help in R, if it says fun, F-U-N, all in capital letters, what they actually mean is function. So some sort of function name, like mean, SD. Okay, so t-apply is actually a function name. But what it does is it'll subset the data for you, calculates the function, and then spits you out a table, hence the name, of the thing you asked it to calculate. Really, if this were a perfect world, I would call this group apply, because that's the point. It separates by groups, or the way we think of groups. It separates by 5 factors, so levels and conditions. So we're going to talk about t-apply And really, the way I kind of have started thinking about this is t-apply the first column, and it has to be a vector. So it has to be a column. You cannot put the entire data set name here because it'll be pretty grumpy with you. It might run something, but it's not super happy about it. So a column of data, and that's really your DV. So this is the variable you want to calculate your model statistics on. So just mean, standard deviation, that sort of thing. So this is going to be your DV, comma, a column or columns of your factor variable to split on. Okay? And they must be factors. If you reverse these two, it will be very unhappy because it will split on every single different variable you have. So if you put a continuous variable in the second column, you're going to get a ton of output, probably a ton of NAs, and it's going to give you a warning, I think. So be sure it's continuous variable DV, not even continuous, it doesn't have to be, DV of some sort, comma, IV, categorical IV of some sort, comma, function name. Okay. And so the function name will be mean, we're going to mean, SD, and length. So first you have to figure out what function you want to use. So mean is going to give you the average, SD is going to give you standard deviation, var, variance, that sort of thing. And let's try it. So there are two ways to do t-apply. And let me show you the first way. So t-apply with the $ call operator. Okay. And if you watch the operators video, it goes over what the heck that is. But basically, the $ allows you to say dataset $column name. Okay. And so R doesn't know what feelings is. Okay, that's actually kind of funny, unintentional. So if I just type feelings down here, it's like, I don't know what the hell you're talking about. But if I type cheese data feelings, $ feelings, it's like, oh yeah, look, you got a whole bunch of stuff stored there. So understanding that R looks at the names of things listed here under data, and if you want to get at one of these little sub pieces, so the column names, or if you're looking at a list, the list names, you have to tell it, hey, it's in this thing, and then go search for this thing. So the $ operator kind of pulls down the arrow and says, look here for it. Okay, so you cannot just call it the column name. It will not work in the way I'm about to show you. So let's do t-apply. We're going to use the cheese data, so the entire data set. So our blah and yummy data set was for subsetting. We're going to leave them alone. I'm going to use now, this first one has to be my DV, and so that's going to be my cheese data, so their rating of the cheese. Second column has to be my categorical variable, which is feelings. Now let's run the mean. So let's see what that does. So it gave me the two means, same means I had earlier that we calculated up here. So 31, 29, 31, here, 29. And now here they are in a little table. That's much faster. It's one line of code instead of 4. And so it calculates the means of the separate groups and then spits them out in a table for you. There's another way you can do this. This isn't really in the notes. So this is t-apply with the with function. So the with function is a nice little function that allows you to say this entire line of data, or I'm sorry, this entire line of code should use this data set. So it's a way to specify the data set at the beginning and then not use it again. So let me show you. So I've got my cheese data, so that's my data set. So the with function is always with data set. Let me just write that here. With data set name here, comma, do your function. So we did the data set name. Now I'm going to do t-apply. Since I've already told it the name of the data set, I can actually remove it from here. So I can do cheese, feelings, mean. A lot of people like the with function because it allows you not to type these like this cheese data only is typed once instead of multiple times. I love the with function as well, but I think when you're learning, it really helps to know both of these things. because it can be confusing. So if you think about subset, the subset function, it did subset dataset name and then column name. And I wasn't required to put the $ operator here because the dataset name is here, and that's the way that subset works. So I think it's helpful to know that tapply has to be on a column, and so this column denotation, and it has to have a column of IVs or categorical variables. And once you get the hang of like which ones have to be columns and which one don't, then you can start playing with the with function. Now it is faster to type, clearly. So I'm going to do everything this way right now, not because I like to type cheese data, although it is fun because it's cheese, just because I think it makes it clear what type of data has to go in that particular spot. Okay. All right, but you can do it with the with function as well. All right. All right, so what if I had two factor variables? So let's say I had a between subjects ANOVA, a factorial ANOVA, so I have two categorical variables. So real quick warning about levels versus conditions. Okay, so if you have one independent variable with different groups, those are considered levels. So levels are the different names for your different groups within your IV. So the overall IV might be gender, and then the levels would be male and female. If you have two or more independent variables that are categorical, their combination is called a condition. So I still have my levels of male and female, and now I've added a second variable of handedness. I still have my levels of right and left, but when I combine those in a totally between subjects design, people can only be in one group, so they can either be males that are right, females that are right, left-handed males or left-handed females. So the conditions are each variable separated out. I'm sorry, each variable combination. So be sure you're watching out for, is it asking for levels or conditions? And this becomes very, very important when you do factorial ANOVA, because this is how the analysis is run as well. So it does level, level, and then conditions. Okay, so this is an interaction. These are main effects. So with tapply, you can do multiple variables. And if you're a little familiar with R, this will be a surprise because you don't use the concatenate function, which is such a pity. You're going to use the list function. So we're going to make a fake variable real quick because I don't have two IVs in this data set. I only have one. I have feelings. I don't have two. So let's make a fake variable real quick. So what I'm going to do is call this my second variable. And I'm actually going to repeat 1 and 2. So the colon operator just means give me 1 and 2. So if I did that real quick down here, you can see that gives me a little vector of 1, 2. I'm going to repeat that 50 times. Because I need at least 100 participants to be the same length as my cheese data. So I'm going to repeat 1 and 2 50 times. So 2 numbers times 2 is 100. Now in the notes I have the C function around it, the concatenate or combine function, but that's because I do that all the time. It's not necessary for this particular data type because repeat handles that, but if you want to put C around it, it won't hurt you. Okay. So what did that do? Well, it gave me a variable, a vector variable that's 1, 2, 1, 2, 1, 2, 1, 2, which is perfect because my feelings variable is 1, 1, 1, 1, 2, 2, 2, 2, 2. Okay, so I just created myself a real quick fake variable to be able to show you tapply with multiple variables. Okay, multiple independent variables. Alright, so we'll do tapply. Still got to be the dependent variable or the data set or the column that you want to calculate the mean on. So that's cheese. Now this is the weird part, it's list. So we're going to make a little mini list of variables to go through. Instead of concatenating the variables into a vector, what we're going to do is use the list function. And this is probably, to me, what, after I got familiar with R, was expected it to be C because they do everything with C, but it's not. It's the list function, which creates this little mini list. If you don't know what a list is, you should go back and watch the object types video. Is I'm going to list my two variables. Well, one of them is my feelings variable, lowercase, and the other one is my second variable. Why does that not have a data set name? Well, because it's not in a data set. Look down here. Value second is stored as a name here, so I can call any one of these things just by name. And it's a separate vector of data. So it doesn't have a data set name at the front before a $sign because it's its own column. It's a separate thing. If both of your variables are in the data set, be sure you use this operator. So after that list, I'm going to do a comma and then calculate the mean. So it's the same format, divs, plural, function. So what that does, very conveniently, is it gives me a little table of the conditions. So it gives me my blog group and my Yummy group by my second 1, 2 variable. So it allows me to calculate the conditional means. If I use one variable at a time, it's calculating the level means. By listing them together, it allows me to calculate condition means. And more. You can do standard deviation as well. All right. So now moving into standard error. How can I calculate standard error? Well, standard error is not a base R function. There are packages that include a standard error function listed as SE. But if you wanted to do this on the fly, it's actually not that hard. So we're going to take the formula, which is standard deviation divided by the square root of n, and use tapply to calculate standard error in a flexible way. So let me talk about n real quick. So remember, n is the number of people in each level or each condition, depending on how many variables we're working with. Big N is actually the number of people overall, so this should be little n at the moment. So the number of people in each group. You could hard code this. So what does that mean? Hard coding is when you type in the number directly. So you know you have 25 people in each group or 50 people in each group, and you just type standard deviation divided by 50. That's perfectly legit. As you get better at coding, just in general, you don't want to do that, because that really limits what you can do. I am a forgetful person. And so let's say I'm working in my research lab and my advisor says, hey, you got 10 or 15 people. How's that study going? So I type myself some code, I hard code it, and I say, oh, the effect size is this. Your advisor goes, great, keep running more participants. You get to the end of the semester, you have the entire data set now. You still have your code saved because you're a smart person and you've saved your code. And you just rerun that code. Well, if you hard coded it with 15 people and now you have 100, you've got to remember to go back and change that number later. That's not going to happen for me. Unless I left myself a note that's like, don't forget to change this number, dummy. It's just not going to happen. And so instead, what I'm going to show you how to do is be flexible with your coding. So making R calculate all of the numbers for you, because unless they're numbers that don't change, like a z-score cutoff of 95% doesn't change, it allows you to use that same code no matter how many times you edit the data set. If you add more participants, delete participants, realize that you've opened the wrong data set, that sort of thing. So the way to calculate n easily is the length function. Okay? There are 3 or 4 functions that calculate the number of participants. Length is the most basic. The problem with the length function is it doesn't always do what you expect it to do. So when you calculate the length of one row of data, so a vector or a column of data in a data set, you get the number of items in the data set. So length tells you the number of items, period. But that depends on the type of data. So with one row of data or one column of data, it is the number of data points. So number of participants, what we're expecting. However, if you calculate the length of a list or a data frame, it actually gives you the number of items. But the number of items is the number of columns or the number of lists. So let me show you. Oops, wrong thing. Here we go. So let's talk about length here. So I'm going to do length of, let's say, our second variable. So that is a vector of data. It says there's 100 people. Okay, that makes sense. If I length of my feelings variable, so still one column or one vector of data, 100 people. Now let's do length of the entire data set. That's 2, because there are 2 columns. Okay, so length does not give you the number of rows. Don't think about it that way. It's the number of items in a data set. And later we'll get to in row and in column, which do more obvious things like number of rows, number of columns. But we're going to start with the length function because it's pretty easy to work with. You just have to know what you're putting into it. All right, so sorry, let me go back to my notes here. Right. So if we want to calculate standard error for each level or condition separately, what we can do is use tapply to figure out SD, and then use tapply to figure out how many people are in each group, or you could subset. Okay, remember this is a 2 separate paths, subset or tapply. Okay. And so let's try that with a tapply with the length function. So tapply dv, so it's my cheese, my ratings of cheese. Single IV, I'm going to just go back to working with 1. So feelings. And then length. Okay. Because the function at the end can be almost anything. Okay. So it tells me I have 50 people, so give me a table back, right? So 50 people in each group. Awesome. So now I have SD, I could do SD and I can do N, so that leads us to how do I get their standard errors? So I could calculate SD, which we haven't done yet, so let me do that real quick. So still same way, dv, comma IV, comma SD. Okay, so now my standard deviations, I have my lengths, and so I could just straight divide. So don't pull out a calculator at this point. It's very tempting because we're all comfortable with calculators, but R is a calculator. Make R do it for you. So we're going to be fancy about it and save them. So watch what happens. This is the best part. So this is N here. So I'm going to set N equal to that tapply and save it. So you see over here I got an N values, so it's a little vector, so watch. N is now that same output that it gave me here. I'm going to call this SD here. So now let me just show you what it looks like. Look, it's the standard deviations. We can do the same thing for the mean because we're going to use that in a minute. So data set, oops, spelled correctly. So now I have N, SD, and M saved. Okay, let's look at M. Oops, uppercase. There we go. So I have my mean, my standard deviation, and my number of people. So this is like starting to build me a really nice table for a APA style write-up. It doesn't even have to be APA, but we love tables, so you know, it could be Chicago, whatever. Now let's take the standard deviation the standard error function and just use our variables that we've created. So we've created this SD variable here, and we've created the N variable here. This SQRT is the square root function. So I'm going to do here, I'm going to say SE because I want to save it, and we're saving it for a reason. We're getting there. It's confidence intervals. I'm going to take SD divided by SQRT function of N. The spacing here actually doesn't matter. I just like to kind of make it more spaced out so it's a little easier to see for you guys. So now I have my standard errors. How can I check and make sure I've done it correctly? Well, you could do some math, but it needs to be smaller. So here are my SDs, 7.61, 11.78. Your SE will always be smaller because you're dividing by another number. If you have a really large sample size, they'll be much smaller. If you have a small sample size, they'll only be a little bit smaller. And that takes some getting used to just seeing. But it looks right, so 7.6 divided by the square root of 50. Having a 1-point standard error kind of makes sense. Alright, so now we've got my standard errors. And don't forget degrees of freedom. So degrees of freedom, complicated topic, but basically remember it's the number of items that are free to vary and keep the same model, so the same mean. And generally, the degrees of freedom formula is n minus 1, so number of participants within each group minus 1. So when I ask you, tell me what are the degrees of freedom for group, you could do the length function minus 1, or you can just look at it and go, hey, that's 49. And we'll get into the specifics for each statistic as we go, but that's the general formula. And what I'm really leading to is confidence intervals. So a lot of the functions that we'll use in R will have their own little confidence interval function, or there's a separate confidence interval function. But I think it really helps to know how to do it yourself too, in case the function doesn't, or in case you can't figure out how the hell the function works, which was definitely me at the beginning of learning R. So it was like, fine, I'll just do it by myself. So now, since I have the mean and the standard error, I can calculate this confidence interval. And so remember, confidence interval is a span around the sample mean where you are either 95 or 99% confident. And so if we repeated this hundreds of times, the population mean should be within that range that you calculated. There's a whole lot of brouhaha about confidence intervals right now and their interpretation, but the way I use them in a sense in real life, because this true population mean stuff is great for theoretical statistics, but like practically, how can I use them? And if I'm looking at a set of statistics someone's presenting, and their confidence interval is really wide, I might be a little suspicious because that means that they have a really large standard error. And if you have a lot of error that you can't explain in your study, when you have a really wide range of data, sorry, brain fart. So your histogram will be very kurtotic, like it would be flattened out, so it's platykurtic. Then how should I believe that that mean is an accurate number? So we're going to use the mean as a model. This is very much from the field book. I really like the way he talks about understanding statistics as a combination of model and error, because it forces you to think about the plethora of different statistics in the same way. So ANOVAs and regressions are really not different. But let's say I'm using my mean as a model of the data set. If the range around the mean is 100 points on each side, and the data only ranges a couple, 300 points, you don't really know what the score is. People are all over the place. But if the confidence interval is very small, that gives me a better indication of like how confident I should be about that number. Now, that's not the traditional interpretation of confidence intervals, but it's a good way to think about models. So if the range around the mean is pretty small, you're more confident that that number is accurate. It's an accurate representation of the population, rather than really large confidence intervals. All right, so let's try this. So what we're going to do is use that formula to calculate. A quick note, you actually don't need the parentheses around SE here, but, SE, old habits die hard. So, so you'll need a lower and an upper. R needs you to give it the star. So if you put two things next to each other with parentheses, it'll just be like, what do you want? I don't understand. So make sure you use the multiplication symbol. So I'm gonna try it here. All right, so confidence intervals. This is specifically a Z confidence interval. So I will get let's name them. So this is my upper confidence interval. And it's going to be mean plus 1.96. I'm going to do a 95% confidence interval times standard error that I calculated a minute ago. So let's do lower. This is the mean minus 1.96 times standard error. Why 1.96? Well, 1.96 is the cutoff score for 5% on a Z table, which is a 95% confidence interval. If I wanted to do a 99% confidence interval, it would be 2.58. You can get R to calculate that exact number to a bazillion decimals for you. We always just use 1.96. And we'll do that when we do t-tests because the number always changes. But in this case, I would say it's safe to hard code because 1.96 doesn't change. When we get to confidence intervals that depend on the number of people in the data set, we'll talk about how do I get R to calculate the t cutoff for me. And those are the distribution functions. They will calculate the cutoff scores for you. So let me run those two things. Now the one thing I want to warn you about these is that the confidence interval is actually, for my blog group, is actually 29.46, 33.68, because the mean is 31.57, so it's in the middle. It should be halfway in the middle because these are centralized confidence intervals. But when I calculate these, my upper and my lower are calculated separately. So basically the warning is don't say that the confidence interval is 33 to 32. Those are two different groups. So the confidence interval for blah is 29 to 33, and for yummy is 26 to 32. Because they have very similar confidence intervals. The yummy one is larger because it has a larger standard error. So just this is a convenient way to calculate, but when you write it up, you're going to be lower comma upper and not just like spit this out on paper. All right. So kind of in a different direction, a lot of this is tied to the field chapter 1 and 2 talk about what is the problem with null hypothesis testing. Well, there's a lot of problems with null hypothesis testing. So what do? Well, we talk about confidence intervals and effect size. So effect size is essentially how much should I care? So how practically important is this analysis, this result, this thing? And so there are a bunch of different effect sizes, including D, G, delta, R squared, eta squared, omega squared, odds ratios, Kramer's V. There's a bunch. So I really want to talk about effect sizes within their family. So they are tied to a specific test type or specific combination of variables, which is like tied to the test. And so I just want to give you a basic idea of what one effect size might look like. So they're all different forms of z-scores, which is kind of cool until you get into r squared, but technically r is a z as well, so really they're kind of bringing it back to the normal distribution. If you want to look at ones that are for groups, Cohen's d is the most popular, so you got group 1 minus group 2 divided by standard deviation. Because the test statistic is often group 1 minus group 2 divided by standard error. So that's the formula for t-test. The problem is the standard deviation can be very tricky depending on which research field you're interested in. So for dependent t, there's several different ones, or there's a big argument over independent t's, standard deviation on the bottom, and let's just say it's stupid math. So it's not hard, it's just long. And so the tricky part's standard deviation. So when we get to each test, we'll talk about the effect size that goes with that test. And our research lab has actually programmed a program called MOTE that allows you to calculate these fairly idiot-proofly. And so we'll use a little bit of R because there are some effect size packages in R that are pretty good, and then talk about how can I do the more complicated ones in MOTE without having to learn any math. But that's a basic idea of an effect size. And why am I just sort of throwing effect size in here? Well, really I wanted to get to power. So Power is the ability to detect an effect if it's actually there. So if the null is false, can I find the effect size, or the effect, not size. And generally power is used as a prerequisite. So you want to calculate how many participants do I need to find this effect, is the way that we tend to use power. There's been a lot of research about replication and this replicability crisis, and so not running an underpowered study. And also, let's say you're working on your thesis and your advisor's like, that's a good idea. How many participants are you going to need? You going, I don't know, 20 is not a good answer. So having read everything to propose said thesis, you've seen a lot of effect sizes, hopefully. And so you can calculate how many people you would need given previous research. So you come with them and says, well, if it's a medium effect size, I need 57. Your advisor goes, cool, that's totally doable. You should do it. But if you come in and you say, given these effect sizes, I need 475, they go, maybe not a good idea. We should try something else. So it's a good way of also practicality of a study. So gpower is a free program put out by the University of Dusseldorf, and I cannot pronounce any of their names. So gpower is awesome. You guys are awesome. Sorry, I'm not German. So you can download it by searching for gpower. If you're on a Mac, it does this lovely thing where it cuts off at the bottom, but it's still totally useful. And so I'm going to talk just very briefly about how it works and try to get you into using gpower. If you are an SPSS person, there are gpower instructions at the beginning of nearly every one of my SPSS videos. And as I add more R videos this semester, we'll do more of this. So if you're wanting to see it, search for the specific test type and I can show you how they work. But the basic overview of gpower is it has a list of test family. All of this is available actually through the drop-down windows too, but I forget they're there, so I always use these. So the test family, so you got exact tests, like Fisher's exact, that's a lot of chi-square stuff. F, which is ANOVA, regression. T, which is correlation, and excuse me, t-tests, chi-square, different types of chi-square tests, and Z. If you can't find the test you're looking for, do it through the test window here because it's got them broken down. We're going to use t-test for this example. And so I can do a drop down and pick which type of test. So I'm going to do difference between two independent means. So that's independent t. Okay. There are several types of power that you can calculate. And so generally I'm doing this a priori, meaning before I get started. How many people do I need? But there are other options in case you get asked to calculate achieved power. Alright, so generally you want to click two tails because most of us consider a one-tailed test cheating. You want to come up with some sort of effect size. This is probably the hardest part for students. I tell them, look at previous research. That was the point of all that reading we made you do. And if you hover over the window, it actually gives you the conventions. Now, a quick word of warning about the conventions is they really should be taken in context with the types of studies that you're doing. So if everybody in your area is getting a 1.5, yes, that's considered large by traditional conventions, but within your own field, that might be normal. So you might consider that maybe, okay, it's medium effect size. And so Cohen kind of warned people like, I'm going to give you some numbers, but remember, it depends on what field you're working in. So he even says he shouldn't have written those conventions out, but I think they're a good place to start when you're first learning and gives you a good reference point. If you don't know the effect size just off the top of your head, you can hit determine and it'll actually calculate it for you, which is pretty awesome. So I have those means from a minute ago. If I can get Studio to come back up. So I have 3157 and 2960. Okay. I've got my standard deviations as well. It's got 7.61 and 1178. I can hit calculate transfer to main. You could just hit calculate, but that doesn't do as much as you want, so hit calculate and transfer to main. So it gave me the effect size. This is a small effect, and then it actually plugged it in over here for me. So it took my number that I was calculating and plugged it in over here. So you could calculate it if you have a very specific set of data you're working with. Generally in an a priori situation, you're doing like an average effect size. If you have zero idea, go for small, because small will be the most number of people you need. Maybe calculate a medium and maybe do the middle of the two, somewhere between small and medium. But if you want to overestimate for power purposes, go for small. The alpha probability, that's what we traditionally think about as p less than 0.05. That's alpha, it's type 1 error. Most of the time we do 0.05 or 0.01. The power probability, industry standard is 80% power, because beta, which is type 2 errors, generally we think of as 20%. Now this will vary, but that's what psychologists tend to do. And then the allocation ratio is used when you you're going to have one group larger than the other. So if you're doing gender at all, at least here in the Midwest, we have problems getting men to participate. So the ratio is about 60 to 40 generally. So I could say it's a 1.2 allocation ratio. It doesn't matter which way you divide, it just changes what output you get over here. So let's leave that alone. Say, okay, it's going to be 1 to 1. We're going to have a perfect world with equal people in each group. If you can't get to the click calculate because of the way that this renders on a Mac, just hit enter in any one of the boxes with your little cursor clicking or blinking, and it'll do it for you. It creates you a very beautiful picture of two normal distributions because it's T, and then tells you the point at which beta would be 20%, alpha would be 0.05, and power would be 80%. So I love these little pictures, they're cute. And then it tells me how many people I need in each group. And then in case I can't add, it actually tells me how many people I need total. So I would need 800 people to find a statistical difference if it existed with a small effect size. If I know I have a larger effect size, so let's go 0.5. Now it's down to 128. So remember, power is influenced by the number of tails, but most people consider one-tailed test cheating, so we don't tend to do those. The effect size, which is supposed to be independent of sample size, and often you can't change it. Now you might be able to manipulate the study to make it more powerful to get a bigger effect size, but I don't know how much control we have over effect size sometimes. Alpha, which most people consider changing, is cheating, and sample size. So the biggest thing you have control over is sample size. And so that's why we would want to calculate that, because it's not easy to manipulate some of these other numbers. And for fun, let's do 0.8. That would be a large effect size, devoid of any context. And now I'm down to 52 people. If I change this allocation ratio to 0.5, so I know I'm going to have twice as many in one group as the other, it's still 58, but now it's shown me like the minimum I need in my small group to make this happen. So that's really useful if you know you don't have equal sample sizes. So it's gpower for an independent T. And then this slide covers all of that, and then gives you some examples of what the pictures look like. But as we go through different statistics types, we will cover how to use gpower more in depth. But it's a really fantastic program that does sample size estimation for you, and actually will estimate some basic effect sizes for you. So that covers everything from confidence intervals, the length function, t-apply, subsetting, standard error, and power for like basic statistical purposes.